Hello everyone, so today in this video we will be looking through obtaining the specific volume provided the pressure and temperature of the substance using the Cardano's method. So on the last video we derived the polynomial equation for the cubic equation of state in terms of z, which is the compressibility factor, right? So in this video, we will be looking through the Python code and we will try to write a code that will derive the specific volume provided the pressure and the temperature. So now here if we look at this side, we have all the equations we need to solve our cubic equation. So if we look to our diagram, so we'll be using the same collaboratory file. So if we look to our diagram, we can see that in these temperatures, our function will have three answers. So it'll cross it here, here, and somewhere there. And there is a place where it will hit our diagram only once when it is in its critical point. So for determining the specific volume, we will look at the two cases where we have three different three different real numbers and only one number. Okay, let's just first define write a function that would calculate us the roots x1, x2, and x3 for the first case and only x1 for the second case. Okay, so we'll just say it's gonna be what? Let's say it's gonna be cubic. Sorry, cubic. It's gonna be cubic roots, and they're gonna take values a, b, and c. A, B, and C. We have like one with next to our z cubed value, so we don't really need that. Okay. So here, if we look at this, for deriving the first case where we have three real roots of the equation, we need the value for q and r and theta. So to determine that, we're going to have to use these three equations that will calculate us the value for q, r, and theta. So we're going to say q equals a squared minus 3 times b, which is excluded volume, over, which is the value that this function takes, and over 9, right? So this is our q, and for the r, we're gonna say that it's gonna be 2 times a raised to the power 3 minus 9 times a times b plus 27 times c, and it's divided by 54. And for our theta, so first of all, we have to look at this and check if our r squared value is greater than the q cubed. So if it is greater, it's gonna have three real roots. But if it's not greater, it's gonna have only one root. There's only case where it has two imaginary and one real number, but we don't need that because we can't have imaginary volume. So let's just use the conditionals to check the relationship between r squared and q. So if it is less than q to the third power, we're gonna say that it's gonna have three real roots. So we have to calculate theta now, which is gonna be numpy arc cos of r divided by q raised to the power 3 over 2, right? And for our roots, we're gonna have three roots, right? So here we can say that all of them are gonna have the cosine number, but they're gonna have different things inside of the cosine, right? So let's just write it in this term, like as an array. So we can have that like all of them are gonna have -2 multiplied by q to the power of 0.5, right? And multiplied by numpy cosine. And here inside of it, we're gonna have our array. So we're gonna have the first value, first thing, which is gonna be theta over 3. Oh, everything over 3. The second term, which is gonna be theta plus 2 pi over 3. It's gonna be theta plus 2 multiplied by pi over 3, right? And for our third root, we're gonna have theta minus 2 multiplied by mp pi over 3, right? So we're gonna have our array and minus at, at the end a over 3. So this is gonna be the, if we try to run this, we're gonna have our output as the array, like array that consists of three numbers, which would be the three roots for our like the function, and for our equation. So we're gonna have to return, and here for our Cardano's like method for our Maxwell construction, we're gonna have to sort our volumes in increasing order. So we're gonna have to start from the lowest to the greatest value. So we're gonna say that return. So in NumPy and working with the arrays, we have a function sort, and if we say it's gonna take our, let's say it's gonna be our root. If it takes our root and sorts it in increasing order. So let's say if we check it, like if we have a and a equals let's say numpy array equals, let's say if we have 0, -1, -2, and 3, and we run like numpy sort numpy array. So it's going to sort our values in an increasing order. So we don't need this. So this will be our first case. And for our second case, we're going to say it's else. So we don't need any other options here. It has to calculate the value for A. And here this thing's SGN is the sign of our value R. So we're gonna express this as, there is a function numpy sign, which is exactly the same as this. So it's gonna take our sign of R and multiply it. We're going to have a big parentheses for the power so that we don't miss anything. And numpy absolute value of r plus, we're going to have r to the squared minus q to the cubed and raised to the power 0.5, right? And after calculating a, we're going to have to look at two possibilities for our b. So we're going to say b will be equal to 0 if a is equal to 0, and else it's going to be equal to q over a. So this is our value for b. And our function has to return, as there is only one solution, a plus b minus a over 3, right? So this is our function for deriving the for solving the cubic equation. But as we have our cubic equation in terms of z, we have to set up another function that would determine the value for the specific volume using the value of z. So let's just run it. So let's just define another function. It's going to be cubic volume. And it's going to take our take the value for pressure and T. We can make it also like specify the method where that it can use. But for this task, we are using the SRK method, which stands for Sauve-Redlich-Kwong method. So we're going to have our A, B, sigma, and epsilon, and sigma from our here cubic AB ES function. So this function was written to calculate the AB, epsilon, and sigma values, right? So cubic ABES, which is going to take T, right? And we're going to have to calculate our beta value. So for the pressure, so we need to calculate this value root to find the roots. So it's going to be beta is going to be equal to B times pressure over R times, it's going to be big R, T. So this is our beta, and we have our Q, which is equal to A over BRT. So we're going to have our Q equals A, which is the sphericity of our molecule, multiplied by B, which is the excluded volume, times R, the constant, and temperature. And this function has to take the values for z from our cubic roots function. So we're going to have cubic roots, right? So there were here in this, like on the previous videos, we calculated our coefficients for the z in our equation. So we're going to have to input that. So for the a, which is the coefficient of the squared z, we're going to input that. So which is, so it's going to be epsilon plus sigma multiplied by beta, right? Minus beta and minus 1. So this is our value for A. So we provided that, and we need our value for B, which is going to be epsilon times sigma times beta squared minus epsilon times sigma times beta squared, and minus again epsilon times sigma times beta. Oh, yeah, like let's say beta. So it's going to be times beta and minus q times beta, right? So this would be our coefficient for the value z in the first power. So now we have to write the constants. So they're going to be minus. So it was, let's say it's going to be minus epsilon times sigma times beta cubed minus epsilon times sigma times beta squared. Oh, sorry for this mistake. Beta times squared and minus q multiplied by beta squared, right? So it's going to be our ABC values for this thing here. And now we have to return. So our function has to return. Here we defined that our V is going to be equal Z multiplied by R multiplied by T over pressure, right? So we're going to say that Z, which is the compressibility factor, multiplied by R multiplied by temperature over pressure. So this is going to be our code that would determine the specific volume using the polynomial, cubic polynomial in terms of compressibility factor, provided the pressure and the temperature. Thanks for your attention.